Good morning, class. My name is Cedric Polk, and I'm going to be giving my PowerPoint presentation, an essay on assistive robots in construction excavators. We're going to start with the introduction, then we're going to move to impair visibility on excavators, perception methods, laser beam methods, LiDAR system, object detection and marking, intelligent visualization, two-dimensional identification, software identification, and the conclusion. I only have 10 minutes, so let's go ahead and get started. This project aims to show how assistive robots can be a valuable tool for operating heavy equipment on construction job sites. Due to the skilled labor shortage in extremely hazardous working environments, there has been a significant demand for the implementation of assistive robots for the construction industry site preparation stage. Due to the extreme reduction in schedule, job site excavation must be accurate to meet the implementation deadlines. Approximately 75% of construction workers are injured every year because of these fatalities involving heavy equipment such as excavators. While on the job, construction workers are at risk of being pinned between other vehicles, caught between barrier walls, and struck by swinging mechanical arms from other excavators. While the aid of assistive robots, the percentage rate of construction workers that are fatally injured can be reduced dramatically in the near future. Assistive robots use state-of-the-art technology to plan precisely where to excavate, where not to excavate, where to avoid objects such as humans and other things that are scattered throughout the area. Without adamant visibility, there is a significantly higher chance of being struck by other construction equipment. Workplace areas can be hard to process on computer software because geographically, they contain highly unpredictable and constantly changing activities. All construction areas must have up-to-date information about the site and the surrounding areas, which can impede modeling and updating. With job sites always having construction workers coming on and off site, there must be a quick visualization involving precise location data for all areas of the workspace at any given time. Insufficient visibility is a major contributing factor in causing casualties at the construction site. An increasing number of advanced vision aid techniques have been recently brought to market. Heavy operating equipment such as dump trucks, excavators, and other heavy equipment have been outfitted with these assistive robots. As we can see in the picture to the right, the shaded area in the gray is everywhere that the operator that sits inside the cab cannot see. Cameras such as high-efficiency fisheye systems produce a comprehensive range of view. These cameras must be mounted at a high enough position that they can overlook any obstacle. Cameras mounted on a rotational platform have an advantage over fixed mounted cameras that will have a limited viewing range and a height that must be shared at all time back to the operator. These images that are shared with the operator produce a three-dimensional both illusion and depth perception at all times. As we can see in the picture to the right, we can see that the fisheye cameras are mounted everywhere viewing the excavator. We can also see that there are cameras mounted underneath for objects that are low to the ground. Laser beam or laser scanning is a very accurate and inexpensive way to produce a map for a job site. Laser scanners can be used like a 365-degree panoramic photo with lasers shooting out from either end, providing a detailed image. Some manufacturers have created a three-dimensional version with color-coordinated markup ability to indicate variations from the intended designs that can be fixed before they cause a scheduled delay that could also have a costly impact. The algorithms that were developed to recognize and register these stationary objects, these are two different ways that the lasers can be used as an accurate tool. The first way is to have a landscape engineer produce a mapped area with the terrestrial laser scanning tool. The second way is to have a laser mounted on the inside of the excavator cab to monitor blind spots not seen while operating. Whether the equipment operator is working on an existing building or starting a new construction project, there must be a detailed map of all the obstacles that are in the way or that lie just below the surface of the earth. The detailed information about the job site shows every nook and cranny. The three-dimensional image that are produced by the lasers are called point clouds. Point clouds are stored on a computer software application such as Bluebeam and computer information design models that can be referenced and used for any model at any point in the construction site. Point clouds give a three-dimensional coordinate plane that can be used at a later date, or the information can be displayed back to a small monitor to the operator in real time. Through intensive research, engineers have created a robotic hybrid light detection and ranging technique made up of two-dimensional scanners called light detection and ranging, or LiDAR. When the Earth's surface has to be excavated, LiDAR will be used for the planning and coordination from start to finish. This will allow for adequately preparing the exact grading of the Earth's surface. These lasers can map out an interactive topographical map by scanning the Earth's topsoil. By using LiDAR, it can measure the distance by the time it takes to reach the Earth's surface and back to the source of the sensor. This increases the surface area covered for the construction site. Operators can use LiDAR in real time for up-to-date tracking, remote monitoring, and finding cost-saving alternative routes for excavation. LiDAR systems can be used to develop estimation of supplies such as fuel costs and other excavation digs before and after construction. LiDAR has been used for a while and has a direct cost advantage when it comes to equipping all excavation equipment with LiDAR systems. The Graphical User Interface Builder, or GUI, uses numerous cameras that are placed around the excavator to observe numerous target requisition objects and tracking areas. The operators do not have to write any code for the equipment information to be shown on the heads-up display. All of the information has to be accessible and readily available for quick and straightforward findings. The working environments with multiple operating equipments have to have a geographical user interface and a two-dimensional camera on every piece of equipment. Inside the operator's cab, there is a display panel for all the information. A video panel on a separate screen next to the display panel presents all the information about the equipment. All of the moving objects that are found in the bounding boxes, like the arm of the excavator, these areas are actively being archived in the graphical user interface as templates. Many scientific studies by OSHA have been produced to find that the best possible solution for terminating the head-down display in all heavy equipment, such as excavators. Head-down displays are placed away from the operator's main point of view so that they can have a full range of non-obstructed vision. This is not the best option due to the increased risk of coming in contact with something or someone in close proximity. Even worse, operators will not use the standard head-down display with all equipment, making it even riskier. Every job site has high margin for error and millions of dollars at risk. All the delivered information needs to be used for a successful operation and completion of a project. The best solution is to provide a heads-up display with an assistive robot in the middle of the operator's windshield. Intelligent visualization is one of the most uncomplicated ways that an assistive robot can be used on excavating equipment. The video camera will capture live pictures of the movable objects on the construction equipment. At this time, the background areas are scanned for depth with lasers from a three-dimensional point cloud software. Model-based automatic object recognition is used to assist excavation operators in helping recognize obstacles and threats. Before model-based automatic recognition systems, these threats were not identified and resolved with proactive warnings before the accident could occur. If an accident occurs on a job site, corrective actions must be put into place. If a collision occurs, it can cause costly delays since replacing the damaged object will compromise the schedule, hence slowing production. Now, assistive robot technology can identify threats and resolve accidents before they can cause harm to anything or any other personnel working in the proximity. A robot is strategically placed to capture video footage by using laser scanners to recognize and register objects. Innovative data scanning systems have been used to update dynamic target objects, point cloud data. A challenge in target recognition from the projected two-dimensional planes is removing figures and analoging them with the respective states of data stored on the file online. Different targets can be prepared automatically by computer-aided design or point cloud systems. Computer-aided design programs and point cloud scanning system correspond with one another to provide a remote sensing technology to the operator. All the information has to be manually entered into a template. Manually entering this information can result in two different problems. The first problem results in a time-consuming process. Semi-automated measurements are calculated to produce input time and data of the implementation. The second concern is due to the user's interpretation and individual variations. The user inputs this information to convert point data into recognizable representation for construction automation. There are different steps for constructing an automated design registration. Processing is the first step in automated design recognition. Then, once the points are processed, the computer-aided design model configures all the information into the database. Lastly, triangular aspects from the database are used for the ununiform resolution model points that are easily to interpret. Automated three-dimensional data is used for determining the challenging transformation areas of the computer-aided design model with point cloud information in the construction area. With the help of assistive robots, operators can use state-of-the-art technology to plan precisely where to excavate, where not to excavate, where to avoid objects, and to avoid other humans that are scattered throughout the area. If there are any questions or concerns, please contact me at CRP0060 at auburn.edu. Thank you.